All right, so let's go through this exam. So this is the first page roughly. So it's very similar to the ammonia problems, but it's planar. Okay, so that gives us a different point group. So I really wanted to kind of keep it similar, but different in a small way. Okay, to see if you could just apply what you know. And so this is not a C3V molecule like ammonia or pH3, but it's a D3H. And that's why I kind of wanted to make sure you didn't freak out on these primes and double primes. So I talked about that on the review day where you had the prime and multiplication rules, and that comes into play if you're doing the selection rules. Okay, so down here it says, refer to figure 1, what atomic orbitals are used to create MO number 1? And so we're looking up here at MO number 1. And this one is the hydrogen A and the B and C. Those are the 1s orbitals here, there, and of course, all around. Now this one on the hydrogen A looks huge. Okay, I was trying to emphasize that it's sort of being used twice here and 0 times here. So this one, MO number 1, is going to have that 2 times HA1s minus HB minus HC because it's got the change in sign for HB and HC. And then that's going to be mixing in with which orbital on the boron? Yeah, so it's it's definitely a 2p. So this is a 2p. Okay, and we got to figure out which one it is. Good job, it's 2py. So here's the y-axis. It goes up and down on the y-axis. And so we look down here and we see a 2s on the boron, so that's not it. So this is how you should take your test. You look at these things that exclude these. So we know that it's not a 2s. So we've knocked it down to 50-50. This has the 2s, 1s on hydrogen A minus the 1s on hydrogen B minus the 1s on hydrogen C. So that part works, and the 2py piece works. And so it's going to be this one. Let's look at the other one. This one says 2px, and so the 2px is what makes that one not the right answer. Okay, questions just as we go along. If you say, hey, wait a second, I didn't get that, because we're really reviewing for the final. Some of these kinds of questions will be on the final. Okay, let's look at MO number 2. This one has the like B minus C, because they're opposite sign, and this is going to be the 2px. So we go over here, we find there's a 2s, that's garbage. Nope, not a 2s there. We have a 2px on both of these. This one has the 2px, and it has that plus 2 on the hydrogen A minus hydrogen B minus hydrogen C. Well, that's not compatible with MO number 2, so this piece is not right. And so it's this one, the 2px plus B minus C. And so then I wanted to get you thinking about ones that aren't shown. So what atomic orbital combination would produce the lowest energy MO? So this MO is not shown, and so that's going to be the one that has the 2s on the boron and the 1s on each of the hydrogens. And all in phase, no nodes. So that's going to be the 2s. Here, this is a minus sign, so we're going to scratch that out. That would produce a node, right? These minus signs would produce nodes. And so here, this one would produce a node. So those are all out. And here's the 2s on the boron, plus 1s on atom A, plus 1s on atom B, plus 1s on atom C. So that's the one with no nodes. That's going to be the lowest energy. Okay. What can I clarify on page 1? Okay, good. All right, page 2. So then we're looking at the Millikan symmetry and Cartesian symmetry of MO number 1. We use that 2py. So if you got that one right and you're thinking, okay, it's the 2py, it's probably the y symmetry, you'd be correct. But even if you didn't get that one right, if you look at this, there's a node that goes here. And let's just say this has a positive end and a negative end at this snapshot of time. And that's very similar to the y-axis. We have a positive end to the y-axis, and if we extend it down, that's a negative end. So it has the same symmetry as the y-axis. Anything that I do with a C3 or a C2 or whatever, it's going to behave like that y-axis. So we come to the character table and we find that y-axis, and it's going to be E prime. So up here we have lots of options. It's not X, so the X's are gone. It's not Z, so the Z is gone. And it is Y and E prime. So this E double prime, that's not correct. So this is the one. Okay, and MO number 2. Again, we'll put a plus and a minus here to show the different colors. And it's got a node here. And you say, but wait, the unshaded one was plus here, but now the shaded one is plus. Remember, those colors will shift like they blink. And so some femtosecond later, the right side is going to be unshaded and the left side is going to be shaded. So really the point is they're opposite signs. And so I put a plus on the right just because the x-axis has a plus on the right and the negative on the left. Okay, so this has x symmetry. Plus it's using the px orbital. So we're looking for x's, so we have an x here and an x here. So the x is on the E prime row, so it's this one. So it's not Y and it's not Z. So we can mark all of those out, and it's not E double prime. Comments? Okay. Now let's do our selection rules. So this, I kind of broke it into pieces. What's the setup for Z polarized light? So if we're going from MO number 1, okay, and the LUMO is A2 double prime. So this is MO number 1, and it's E prime. So this kind of, it depends upon the previous one. And in fact, if you were to look, they're all E prime. So I kind of gave you the answer, okay, for number 4 there. And up here is an A2 double prime. And we're using Z polarized light. So we find Z polarized light, that's A2 double prime. And this top one is A2 double prime. So we find this one here. The top one, the LUMO was A2 double prime, and then the Z polarized light is A2 double prime. So, and then the lower state is E prime. So that's the one that has all 3 on it. Okay. So that's the setup, and then you multiply them using the direct product table. Okay. And so let's do that. So we come over here, we have A2 times E. So we have A2 times E will give us E. So we have E here, and then prime times double prime, that's this one right here, gives us a double prime. And then A2 times E gives us E again, and double prime times double prime gives us prime. And so that gives us E prime, and that's going to be equal 0 because it's not the top row. So we've got this one. Okay, so I'll do the same 2 problems, but with the XY polarized light. And so XY light is right here. Kind of marked it out. So XY light is E prime, and so we need E prime in the middle. And so we've got this one right here. E prime is the MO number 1, A2 double prime is the upper state, and E prime is XY light. So let's go ahead and do that one. E times E is A1 plus A2 plus E. And then the prime times prime gives us prime. Okay. And then I have to take the A2 times all of those pieces. So A2 times A1, so we've got this column here. A2 times A1 is A2. And that's going to be double prime because we have an odd times an even. And then A2 times A2 is going to be A1. And then, let's see, is that right? Yeah. Prime times double prime is double prime. Yep. So A2 times A2 is A1, and then prime, double prime times prime is double prime. And then A2 times E gives E double prime. And so that's going to equal 0, because it's not top row. I have an A1 there, but it's A1 double prime, and this top row is A1 prime. Okay. And so that's this bottom one, E. I can't actually mark on it because PowerPoint's trying to give me my little tools to change the pen color. So, any questions on that one? If you hadn't been sort of prompted about the prime and double prime rules, would that have messed you up? Or would y'all been able to figure that out? Okay, well now you know. So that's why I told you on the review. It's important to come to the reviews. Okay, let's look at number 10. If MO1 were, going to a LUMO of A2 double prime, is this transition allowed? And so basically, we have number 7 here that's telling you the Z is 0, and number 9 is telling you XY is 0, but the allowed or forbidden is not in those problems. And so this is just an interpretation of those results. And so it's no, it's not allowed with either X, Y, or Z polarized light. Now we sort of leave behind the MO theory for a second, and we start looking at local bond theory. So the Lewis dot structure for BH3, what's the hybridization on the B and the HBH angle? So here it is up here. Notice there are no lone pairs because boron only brings in 3 valence electrons, and each hydrogen brings in 1 each. And so we have 6. And so when we put 3 bonds on there, we've used up all 6. So there are no lone pairs, so this is a planar molecule. So we only have 3 domains. And to come up with 3 domains, we have an S and 2 Ps. So it's sp2. Okay, and that's going to give us a trigonal planar of 120 degrees between them. So that's the hybridization and the angle between the hydrogen, the boron, and the hydrogen. And then how many valence band UV PS peaks would be predicted by local bond theory? If we hit this molecule with UV light, there's one type of electron. It's the HB bond. And so it's just going to be 1 peak. Since there are no lone pairs or anything like that, there's no other kinds of electrons in the valence band. There's a core electron in boron, so there'll be some 1s electrons in the core, but we're talking about valence band only. And then, yeah, and so then we completely change gears to figure 2. Okay, so just for, it says here, refer to figure 2, you should label all the energy levels with sigma, pi, sigma star, and pi star. And so I'm going to go ahead and do that here. This is the lowest one is sigma, then sigma star, then pi. And then that's the sigma done with the p orbitals, and then the pi star, and the sigma star. And then these are all connected. And then this is that SP mixing. Although I didn't really ask any questions about it, it's still here in this figure. And it drops down below here when we get to oxygen. So this is that sigma bonding orbital with the p orbitals, and that's the one that moves the most. Okay, so now we can ask questions about our figure. So what type of orbital is the highest occupied molecular orbital in B2? So here's B2. We come up, we see those electrons. Those are in a pi bonding orbital. Okay. So that's going to be pi. What is the multiplicity of B2? We see here that we have 2 unpaired electrons. And so the number of unpaired electrons plus 1 is your multiplicity, so it would be a triplet. If we were to calculate using spin, so S is equal to 2 times the 1/2, right? There's 2 unpaired electrons. And so S is equal to 1, and then 2S plus 1 is equal to 3, which is where we get the triplet. My arrow's messed up. Then we look at the ground state of O2 as a triplet state. These unpaired electrons are in what degenerate set of orbitals. So we come up here and we find these, and those are in the pi star. So here we are in the pi star. And then compute the bond orders of all the diatomics, and what is the bond order of C2. So we can look at this one. This is a bond order of 1. This is a bond order of 0. So we're looking at, there's 2 electrons in the bonding, 0 in the antibonding. Okay. Here there's 2 of each, so bonding minus antibonding is 0 divided by 2. So here we have 2, 4 in the bonding, minus 2, so we're back down to 2. Divide by 2, we get 1. And then the carbon, 2, 4, 6 in the bonding, minus 2 in the antibonding, so we have 4. Divided by 2 is 2, so we can answer that question. So it says that carbon, from molecular orbital theory, should have a double bond. C2 should have a double bond. Nitrogen would have a triple bond, oxygen a double bond, fluorine a single bond, and neon a 0 bond. No bond. So how many peaks would be seen in the valence band UVPS for carbon, for dicarbon? So we come up here and we look at the number of types of orbitals. We have 1, 2, and because this is degenerate, we have those act as 3. So that would be 3 peaks in the UVPS for C2. Now this is the one that caught a few people. They came and talked to me after the test. So if we have C2, we have 2 atoms of carbon, each has 4 valence electrons. And so we have 8 valence electrons. Okay. And then we form a single bond if you want. We can do this the long way. Okay. Minus 2 bonding electrons. Okay. And we have 6 electrons left over. So I'm doing it the really long freshman way. And so then we put those electrons, 1, 2, 3, 4, 5, 6. Okay. And then after we've done that, we look to see if there's an octet on carbon, nitrogen, oxygen, and fluorine. So that's a question. And we look at it and we say, no, we've got, this carbon can claim 2, 4, 6 electrons, and this carbon can only contain or claim 4. So this is a covalent bond, which means it's in the valence of both atoms. And so they both get to claim that bond as their electrons because they're sharing them. And so to form an octet, we need to start making double bonds, triple bonds, and so on. So this is kind of unequal, so we'll put 2 more here, and we'll make a double bond. All right, so this carbon now can claim 6, and this carbon can claim 6. Let's see, 2, 4, 6, yeah. Wait, do I have it wrong? Let's see, 2, 4, 6, 8. No, that's fine. Okay. And so then we need to share more, okay? So if we share these electrons here, we end up with a triple bond. And so this carbon can claim 6, and this carbon can claim 8. So this carbon has an octet, but this one doesn't. So we've got to share 2 more. So this is the craziest one. This is a quadruple bond between carbons. So the octet rule is satisfied. Lewis dot structure. Never seen this before, have you? Because we never ever show this to the freshmen. Okay, because this breaks Lewis dot theory. We don't have quadruple bonds. Okay, and so this is one example where it breaks the Lewis dot theory. I mean, it's following the rules. That's an octet, but we don't ever have any quadruple bonds between carbon atoms. Okay, but that's what you would get if you were to make a Lewis dot structure for dicarbon. Okay, and this would predict. Again, Lewis dot structure doesn't really acknowledge the difference between, these. And what would you even call that 4th bond? I mean, do we have 3 pi bonds? I don't even know how that would work. 2 sigmas? I don't know. So those categories of sigmas and pi's really apply to the MO theory.
How do you know to put 4 bonds between carbon as opposed to leaving it like you did right there with the double bond and then
this one?
Yeah.
Yeah, so what I'm doing when I'm asking how many electrons they can claim, let me change color for this. So when we do a Lewis dot structure, we look at this and we say, okay, let's draw circles around the bonds and the lone pairs and count all the electrons in those circles. So this carbon can claim all of the electrons in its circle. So it can claim 2, 4, 6. So it doesn't have an octet yet. And this carbon can claim 6. So for carbons, nitrogens, oxygens, and fluorines, they are the strongest adherents to the octet rule. And so they're going to make double bonds until they get an octet. So we move 2 more down in, and now this one can claim 8. So it has an octet, but this one can still only claim 6, and so we're not done. Did you see that last part? I saw you start writing. So this one can claim 8 now, but this one can only claim 6 still. And so when we move those 2 down, we shared 2 more with the atom on the right, but the atom on the left didn't get any more until the atom on the right shares. And so this is what we end up with, is this particular structure for C2, which would be the shortest carbon-carbon bond you could have. And in fact, the MO theory bond length, that bond would be longer than nitrogen, not shorter than nitrogen, because it doesn't have a bond order of 4, it has a bond order of 2. So once again, MO theory accurately predicts the electronic structure, and the electronic structure is what gives us the bonding.
I just assumed that I missed this in lecture, like maybe I wasn't paying attention. So, which lecture is this in?
This goes back to the OpenStax book. Yeah. So just the Lewis dot stuff. But I just wanting to show. I mean, yeah, just saying push the octet rule as far as it'll go for carbon, and you're going to get a quadruple bond on carbon. Yeah. Okay. And so then. So let's go down here. How many bonds are between the 2 carbon atoms? Would be 4. And then refer to figure 2. What would be the bond order of F2, 2 minus? So if we put 2 more electrons in fluorine, it's isoelectronic with neon. And so then that would be a 0 bond order. And then refer to figure 2, would O2, 2 minus be paramagnetic? And so if we put 2 more electrons in oxygen, then no, everything's paired up. And so it would not be paramagnetic. Okay, and then we get into the shorter than, longer than questions that I really emphasized on the review, because this one is a little different. We have that NO minus. And so looking at this, I've got a nitrogen and an oxygen. How do we do this one? Well, if you think about O2, if I change one of those oxygens to a nitrogen, it only brings in 5 valence electrons. But then if I bring in an extra one for the negative, then it has 6. And so it's isoelectronic with O2. So it should be the same as O2. So I'm going to go ahead and erase these 2 electrons that I added earlier. And so we're looking at this. So NO minus is also, isoelectronic with O2. So it would have, the bond length would be the same as, if you're just doing like a sketch, whether it be shorter or longer or the same as, it's going to have the same bond order as O2. So the bond length should be the same. The vibrational force constant, again, that's the spring constant holding it together, should be the same as, because that's governed only by the electron cloud. But when you get to the masses, because nitrogen is lighter than oxygen, it's going to be a higher than, because the vibrational frequency is K over mu. And as mu goes down, vibrational frequency goes up. And so then we're making a diatomic MO diagram for bromine, Br2. What orbitals are used in the bonding area of the MO diagram? And so we look at bromine, that is, it's over there on row 4. Okay, so it'll be the 4s and the 4p. Now here's all of the orbitals for bromine. I mean, bromine has all of these, but these are not in the bonding area, okay? And you may say, well, what about the 3Ds? Well, there was no option of just the 4s, the 4p, and the 3Ds, okay? If I'd have left that option in there, you might want to mix in the 3D orbitals because those are valence orbitals too, and that would confuse things, so I just didn't give you both those options, okay? It was either the 4s and the 4p or stuff that's clearly wrong, okay? So I tried to reduce the ambiguity there. Okay, now some drawing. So this one was, I didn't clip the, I grabbed the picture but not the instructions. Okay. So the instructions say draw the pi and pi star orbitals on these molecules. And so this is a planar molecule. It's a C2V molecule. The C2 axis goes vertical here. And that pi bond is out of the plane. It's using these unused px orbitals. Okay, and so that's the pi. And so I'll just redraw the molecule here. And then this is the same kind of thing, only I'll just swap the shading on these. And that's the pi star. Okay. So that was the first piece. Draw those. Now, I don't really know. I mean, I was pretty generous in the grading, okay? So you've got the molecule here, and people would do things like this. They would say, that's the pi. But that's not on the molecule, right? And it says, draw the pi and pi star orbitals for the cis dichloroethylene molecules. There's a molecule given there. So my intention is always for you to draw it on the molecule so that I can see that you're showing me where those pi bonds are. Because I don't know if you're really doing this related to that molecule or if this is just something off your note card, right? It's like, oh, that's what a pi bond looks like, okay? So I gave some points for that, but if it wasn't on the molecule, and even this, doesn't show the chlorine atoms or the hydrogen atoms or anything like that. So I don't exactly know how to grade that. It's not related to this molecule at all. There's a coordinate system here. You know, you're trying to show me that you know on this molecule, this is what the pi bond looks like, okay? Not just what a pi bond looks like, but on this molecule, where's the pi bond? The pi bond is out of the plane. It's the p orbitals coming in and out of the paper, the px orbitals that are pi bonding in this molecule. Now there are other p orbitals. Let's draw this one. Okay, so let's draw the pz orbital. So here's a pz orbital. And that's not, this is where we get into that ambiguity surrounding the polyatomic molecules versus the diatomic molecules. This is not going to be classified as a pi bond. This is in the sigma framework of this molecule. So even though it's side-on interaction, it's kind of like a pi-like interaction for the carbons, it's a sigma interaction for the CH bonds and the Cl bonds. And so this is not the pi bond. So if you go back to organic chemistry, this is going to be, they're going to use hybridization theory to draw these, and they're not going to call this a pi bond either. Okay, they're going to talk about sp2 hybrids, you know, interacting with this. We know from MO theory you don't need to make hybrids. You can just use the pz orbitals to make this kind of arrangement. But it's the one that's out of the plane that's unique, and that's the pi and pi star bonds. So there's only going to be one pi bond in this molecule and one pi antibonding orbital in this molecule. And so those are going to be the ones that are coming in and out of the plane on the z-axis. So let me make sure that you ask all your questions on this, because I was looking for these top two drawings. Yes.
Can you explain why that's more of a sigma bond again?
Because the look where the node is. Okay, the node, for if you were to just focus your eyes only on the carbons, you might say that's a pi bond, right? But they're in the plane with the hydrogens and the chlorines, and so they have to interact with those. And because they have to interact with the hydrogens and the chlorines, they're sigma interactions. Yeah, so that's what makes it a sigma. We call it the sigma framework of the molecule. And for all these extended pi systems and like benzene, think of benzene, the sigma framework is all of the bonding in the plane of the molecule. And the pi bonding is the pz orbitals that come out of the plane. Yeah, so that's how you would make that judgment in like an organic chemist. Now they use the hybridization theory to make the sigma bonds, and then there's unused p orbitals to make the pi bonds. Okay, but we've kind of dashed that local bond theory to the rocks, and so we still though use that language, the sigma framework, to explain that this is not a pi bond, this is a sigma bond, the one I've drawn on the right. Yes, Marie.
So the original molecule you drew planar, and there's the character table. A1 is Z.
Yes.
And so I simply assumed that the Cartesian direction for those p orbitals was going to be in the Z direction. But is it X because of steric hindrance, because of the H and the hydrogens and the chlorines? I'm just not understanding how it was X.
Okay.
Those chlorines are in the X.
Okay, so then we use the molecule to decide on the point group, right? And then because we know this molecule has the C2, I think I'm reviewing. I'm starting from the beginning. So, this is the C2 axis, okay? And so by definition, that's the only axis, the rotation axis this molecule has. So by definition, that has to be Z. So this has to be the Z axis. Okay, and so that sets up this molecule Z axis. Now what sets up the Y axis is in the center mass of the molecule, you have the other two axes coming out. And we have the right-hand rule. And so X cross Y must be Z. So I know where my thumb is, and the index finger is X and the other fingers are Y. And so I rotate my hand around until I see that X-axis is the one coming out at me. The Z is pointed up, the X is coming out at me, so that means the Y is going to the right. And so then this is the X-axis, and this is the Y-axis. And also it just forms that counterclockwise rotation. If you're looking at the coordinate system like this, it goes X, Y, and Z, sort of a counterclockwise manner. That's what the right-hand rule would give you. Okay, now why do I care about the right-hand rule? It's nothing against left-handed people. Okay, it's because the character table was created with right-hand symmetry. Okay, so because the character table was created that way, then we need to make sure our coordinate system matches the character table so that we get X and Y and Z correct in the character table. Okay, now there's nothing at all that connects pi bonds to any of the Cartesian axes. So in benzene, it's the pz orbitals that mix because the z-axis comes out of the plane of the paper. But in this molecule, the y-axis comes out of the x-axis comes out of the plane. And so those p orbitals that are out of the plane are the px orbitals. Just by looking at it, the symmetry. So I have, if this is a carbon atom, I have an orbital that comes out in the x direction. I have an orbital that goes in the z direction, and I have an orbital that goes in the y direction. And so I'm trying to figure out which of those three p orbitals is going to make the pi bond.
Right now, I get that they're the ones.
Yeah, they're the ones coming out of the plane.
I
Yeah.
get that because of the wedge and everything. But so we should have known that those p orbitals were in the x-axis because of the original symmetry, which you said Z is going up and down, and
Yeah.
C2 rotation around about the
Yeah, that sets up the Z-axis. And then why not the PZs, right? This is side-on interaction. I think this is what kind of McCall was asking. This is a side-on interaction, but these are in the plane, and they have to interact with the hydrogen. So that sets this up as a sigma bond. Because it's interacting with these hydrogens, those p orbitals are, this whole thing is one molecular orbital, and it would be a sigma. It's primarily sigma because it's the carbon interacting with the hydrogens and carbon interacting with the chlorines. And in fact, that's one here. This is one molecular orbital that supports the CCl and the CH bonds. So I could have drawn that one. A lot of people did draw that one for the bonus. What about the py orbitals? Well, those would be sigma between the carbon-carbons. So you would have this kind of this molecular orbital here for the py's, but then you also have those hydrogens, and so those hydrogens and chlorines could be in phase with this as well. Since they're in the plane, then they have to interact. And so this would be one that supports the bonds of all four of the, CH and the CCl, and it actually strengthens the CC bond too. And it has two nodes. So this one would be higher energy than the one above it. But so I guess the PX, the PZ, the PYs, those would be interacting with those hydrogens and chlorines. And so in a larger organic molecule, when we talk about the double bond, we're really talking about that bond only being a double bond. So, if you've got some extended chain like this, right? Those double bonds are going to be sticking out of the plane of the paper. There are other p orbitals, but those other p orbitals are in the plane, and they're going to be interacting with the sigma framework of that molecule. The pi bonds are all side-on interactions with those p orbitals that are sticking in and out of the plane of the paper. So whatever, if we looked at this molecule, let's just say it was the same coordinate system, x coming out, y there, z here. Okay, it would be the px orbitals making those bonds. Yes.
So the answer for what carbon orbitals are involved in the pi and
pi. So those would be the px orbitals.
Just 2px. That's
2px orbitals. That's the answer. Yeah, 2px orbitals. Yeah, and then what Millikan and Cartesian symmetries of these two orbitals? So they would be, the pi would be x symmetry. So we would put x there, and then we find x in the table, and it's B1. And then this one is x times y. So x times y, and we find that on the table, and it's A2. So those were the answers for the next one, the Millikan and Cartesian symmetries. Now this is x times y. If we were to look down on this, you'd see the xy plane has the plus minus pattern. And then let's draw this one down here, the bond molecular orbital that weakens the CCl bonds. It's easy for me to draw s orbitals, right? They're just circles. And so in this case, we'll draw the molecule. And so if I take the 3s orbitals on the chlorine and the 2s orbitals on the carbons and the 1s orbitals on the hydrogen, I'm just going to put them all in phase and out of phase so that there's nodes everywhere. So I want to break every carbon-hydrogen bond and every carbon-chlorine bond with a node. And so it doesn't say anything about the carbon-carbon bond, so I could leave those the same. But if I shaded all of these, then I've got nodes that break all of those bonds. And so that would be one of the options. And I just thought I'd ask you to draw two of those orbitals because of time, and give you the choice of which ones you drew. So. Oh, and then lastly, it says show if the pi to pi star transition is allowed. Okay, so that's we need to determine whether the B1 to A2, oh goodness, is allowed. So let me erase all of this stuff on the right. I love this tablet. Goodness, all these little marks. Okay, so let's start up here at the top. We have B1. Ooh, I'm going to run out of time. I didn't think I would run out of time. Okay, so we can go, X light is B1. So B1 and B1 is A1, and A1 and A2 is A2. Not allowed, right? Because it's not top row. Okay, then we have, for Z polarized light, we have an A2, an A1, and a B1. Okay, that's going to give B1, and this is going to give B1 times A2, B2 equals 0, and so that was Z polarized light. And then the Y polarized light, we have A2, B2, B1. B2 times B1 gives A2. Woohoo! We got it. Because then we have A2 times A2, that gives A1. Not equal to 0, so Y polarized light is allowed. And then the last page is the MO diagram. There's no way we could do that, but you've seen plenty of those and answered all those things, and a lot of people did really well on that part. So just bring all your tests up and pile them on this pile for me. And the evaluations are open this week, so they're on Blackboard.
Would it be okay if I'm going to take a picture of him?
Yes. Oh, did you just come in?
I came in a little bit later.
Okay, let's go to the hallway. So they'll just pile them up.
Dr. Williams, do
Yes.
you happen to have the exam 4's